Welcome to Lecture 9, Astronomical Instruments. If you're following along with the course syllabus, you'll notice that we are right at the breaking point about a third of the way into the class. As I promised at the beginning of the class and tried to warn you, unfortunately we had to spend quite a bit of time on background information, building up terminology and some of the basic and studying some of the basic attributes of things like light that we'll need to know in order to understand how and what we can discover about the universe. Today is kind of we come very near the end of the introductory third or so of the course as we talk about astronomical instruments, which is a fancy way of saying mostly telescopes. Once we do that, then we'll be in a place to actually take the next step into analyzing starlight, which will form the majority of the next three lectures. And that's really where we start squeezing as much information out of the light that we capture as we can. So with that, let's go ahead and jump in. So if you remember, and I keep referring to this, but in the very first lecture, I made the claim that that astronomy could be argued to be the oldest science, and the reason is that all it takes is your eye to make observations, and as you know, is fairly obvious, for the vast majority of human history, the human eye is the only observational piece of equipment, if you will, that astronomers had at their disposal. So we're not going to, this is not a class in human anatomy, but it actually is helpful to at least look at the basic anatomy of the eye, because it turns out that as throughout history, starting in the 17th century and then on to, to today and beyond, the development of telescopes uses this as its template, and so if you look at sort of the main components of the eye, what we're going to be focused mostly on is the lens here, which is the focusing piece of the eye. And of course there are others, the iris, the pupil, and the cornea, and then the retina at the back of the eye, which is sort of where the image gets projected onto. And so, as I said, for both the most rudimentary telescopes and the most impressive modern telescopes, they all have analogies to these, with some caveat with regards to the lens, and we'll say more about that coming forward. So anyway, this is the oldest telescope, if you will. It's the one God gave you, and light comes in through the pupil. So the pupil is what we'll very often call the aperture, which just means it's the opening. It's where the light comes through. And then in the case of the eye, it is focused by the lens. So the rays of light that enter the eye are bent by the lens in a process, through a process that we'll talk about in a little bit. And then, as is noticed here, or as is denoted here, and is worth mentioning, the image, the arrow here on the left, which is the object, that you're looking at, is right side up. The arrow is pointing up, whereas the image as it's projected onto the retina is actually upside down. And that's true. It turns out that your eye or your brain flips that back around for you, so in your perception, we perceive things properly. But it is the case that it gets flipped upside down here, just because of the way that the light rays are bent through the lens. So anyway, that's the oldest piece of observational equipment for astronomers. Now, I've made this comment before, and the precise numbers that are quoted here will be different from one book or set of slides, one lecturer to another. But the human eye is sensitive to lights of a particular wavelength, and sometimes you'll hear those quoted as between 400 and 700 nanometers. Here, I say 350 to 750. The reality is that different people's eyes have slightly different sensitivities, and so some people will be able to see something that others will not. It's kind of a fuzzy range or fuzzy cutoff when you get to either end of the range, but it's a particular range of wavelengths that define visible light. Okay, so we can only see, there's light, as we've talked about in the context of spectra. There's an infinite number of wavelengths outside, either at higher wavelengths or lower wavelengths outside the visible range. And now we know how to, we build telescopes to capture those, and we can actually learn a lot about things outside, out there from light that's outside the visible range. But certainly, historically, before advanced technology came along, we were stuck just making observations with our eyes, and so we were restricted to studying those those wavelengths that were in fact visible. To introduce a term that we're going to be using, angular resolution is a term that means how close can things be before before they sort of merge together, right? So if you imagine if you have 2 points, say a foot apart, that are a foot away from you, you can easily tell those points apart. But if these same 2 points are a foot apart and you move them a mile away, now you're not going to be able to see them apart anymore, right? And so, and we'll have some more examples here. But the angular resolution means what is the minimum angle between two objects that you're viewing, which you can tell apart. Because obviously, if they're very far apart angularly, if they're 45 degrees apart, as viewed from your vantage point, then they're very easy to tell apart. But the closer they get, the harder it is, and at some point, you can't tell them apart anymore. And so that angular resolution is something that we're going to refer to a lot today, because it's sort of the defining characteristic of how good a telescope is, or it's one of the defining characteristics. The higher angular resolution is, the better the telescope is, right? Because you can see better. And so if you have very good vision, then you can resolve things well, and if not, then you can't. So for the human eye, the angular resolution is limited by the size of the pupil. And the pupil, again, is just, is the aperture of the eye. It's the hole through which light comes in. And so the smaller the hole is, the lower the resolution. The larger the hole is, the bigger the resolution. And this is something that we're going to come back to again and again, again in the context of developing bigger, better telescopes, because the larger the aperture is, the more light you can get in, the better resolution you can get, the better images you can get, and the more information you can get. So the telescope, is without doubt the most important piece of astronomical stuff, right? It's the most important apparatus ever developed in the context of astronomy. And we've talked about it a little bit, but they kind of came on it. They were, it didn't come out of thin air, right? Eyeglasses, for example, were created first around 1200 AD. So, and this was something before I taught this class, I had no idea they had been around so long. And they were mostly used as reading glasses, just as magnifying glasses, basically. People realized that, hey, if you curve glass in a particular way, you can make things look bigger. And so, so reading glasses started to be a thing almost 1,000 years ago. And it's impressive to me that they were able to grind lenses smoothly and actually accomplish that. Obviously, that technology improved over time. But it took several hundred more years before it occurred to anyone, to use this technology, which basically already existed, at least in part, in the context of glasses, and apply that to the sky. Now, you will very often hear, and you will probably even hear me say this a couple of times during the course, so I try to caveat it a little bit. You'll very often hear Galileo credited with the invention of the telescope. And there probably is a sense in which that's true. There may be a sense in which it's not true. But the reality is that there were a couple of different people in the early 1600s, first decade of the 1600s, that did very similar things. There's no question that the technology that was in the earliest telescope that Galileo used was not developed by him. So the technology itself was not developed by him. In fact, what became telescopes and what Galileo used was first used on the sea, was used by ship captains, so that they could see out farther and maybe tell if there's they see a spot on the horizon, a ship coming, and they want to see, is this friend or foe? Is this a pirate ship, or is this another merchant ship? So on. Well, and certainly you can see land more easily as well. So you can see there are a number of applications for these magnifying objects or devices in the context of shipping. But Galileo had the good sense to just take that and point it up. Okay, and so that's the extent to which he invented the telescope. But certainly once he recognized the value of that of telescopes, he certainly started developing his own. He built his own, and he took it and ran, as it were. And they did three particular things that were just sort of, mind-boggling in terms of the advances that they made, even with the relatively rudimentary technology they had at the time. The first is that the number of faint objects that were visible just exploded. So, if you go outside on a dark night, you look up and you see there are a lot of stars, but there's a lot of empty space too. A lot of just blackness in the night sky. When you look through a telescope, Galileo immediately discovered that there were a whole heck of a lot of other things that were just too faint for him to see with the naked eye. But with the magnification provided by the telescope, he was able to see a lot more. So that's the first thing. The second thing is that those objects that he could see, even those that he could see with the naked eye, were bigger, right? And that's one of the big advantages of a telescope, is it just makes things bigger so that you can see detail in a lot. You can see a lot more detail. And then finally, the angular resolution of the objects increased. So he was able to distinguish between things that to the naked eye were indistinguishable. So you might just see, for example, you might look up and see a dot of light in the sky and say, there's a star. I'd like to see that a little better. You look in through the telescope and you see, in fact, these are 2 stars, or even 3 stars that are very near each other as viewed from the Earth. But with the eye, they can't be resolved, whereas with the magnification and the improved angular resolution provided by the telescope, you can. And so these were 3 things that just, it was like flipping a switch in terms of his ability to see things. Astronomy had been around for a long, long time, obviously, in terms of observations made around the world by every ancient culture that we know about. But none of them could see. All of a sudden, Galileo was the first and the only person in human history to be able to see all of these new things. And so it was a great time to be him, because anywhere that he pointed the telescope, he's just gonna discover something new. Now, the early telescopes used lenses, as I mentioned, and we'll say more about the lenses and other ways to construct telescopes. But certainly lenses were the first main component, the key component of the earliest telescopes. And those lenses were made of glass, and they bend light using a property known as refraction. And refraction, it turns out, is a property of every kind of wave. So sound waves refract, light waves obviously refract, water waves refract. And refraction is just a fancy word that means waves bend, they change directions when they move from one material into another. And we very often will refer to materials as media. Medium is the singular, media is the plural. So when a wave moves from one medium to another, it will bend. How much it will bend will depend upon the speed of the wave in those 2 different materials. If this were a physics class, we would spend some time on the details. That turns out there's a mathematical equation known as Snell's law, which relates the angle of incidence to the angle of refraction, and you can actually calculate exactly how the waves will bend. For us right now, we're going to focus on the qualitative aspects, and so we'll very often, well, to the extent that we do this, we're not going to draw a whole lot of pictures like this, but what's being shown here is that the green represents a beam of light, and these red lines, which are perpendicular to that beam, are known as wave fronts or wave crests. You could think about it as being the peaks of this wave. So if this is a sinusoidal wave, with peaks and troughs, you can think about these red lines as denoting where those peaks are. And so the wave is traveling from air into glass, and it bends then as it enters, and then it bends again when it exits. And one way to think about this, why this would happen, is just that as the wave front enters the new medium, as it moves from one medium to another, part of the wave front enters the glass first, right? Unless the light ray is moving exactly perpendicularly to the surface, part of that, and in this case, the left part of the wave front will enter the glass before the right part of the wavefront. And that's important because it turns out that the speed of light is lower in glass than it is in air. And so as a result, the right part of the wave crest is moving faster now than the left part, because the left part is in the glass and the right part is still in the air. And so the result is that the wave front bends. It's a lot like driving a car, you know, where one of your tires ends up in mud and the other part is still on a paved street, right? You're going to end up turning towards the mud because your tire that's in the mud is not going to be able to travel as easily. And so it's exactly the same, you know, basic mechanism that happens here. And it gives rise to some very useful results that that Galileo captured and exploited, and many others after him. And it also does some funny things, just like, you know, making the pencil appear broken, because the light is bending as it comes through the water, or as it leaves the water and enters the air. The light is refracted, it bends. And so it turns out your brain, when we decide where an object is, we basically track the light rays backwards in a straight line, okay? Because our brain knows that light travels in a straight line, unless it doesn't. And it doesn't when it bends coming out of a medium. And so we can spend more time talking about that particular phenomenon, but the basic mechanism is just what I've said. When any waves, and for us light, changes media, moves from one material to another, it will bend. And it will bend by a specific amount that we can calculate. And so, you know, more to the point here, if we take a lens like this, we can focus the light using that lens in a particular way. And so, for example, if we wanted to focus the light in a specific place, we could construct a lens to do that. And so in this particular case, you can see you have rays of light that are parallel to one another coming in from the left. They all bend. They bend by different amounts depending upon, you know, where they hit the surface of the lens. But then they are all focused down into a point, which, not very creatively, is known as the focal point. And we'll say more about that. But this is going to be the main feature. This is the utility of lenses. This is why lenses are useful, and we'll see the applications shortly. So there are two main types of telescopes, and I sort of alluded to this, and we're going to get into the details now and in what follows. But the first type of telescopes that use lenses are known as refracting telescopes. And again, it's not a very creative name. They're called refracting telescopes because they use refraction to focus the light. They use lenses made of glass to focus the light. And so, you know, in a not drawn to scale schematic here, we have light that will come in from a very distant star, right? It will come, and those rays will be parallel to one another because they're coming from so far away. You know, they're going to be parallel rays. They will enter the lens and they will be refracted, and they will be focused down to a point or onto a plane that we call the focal plane. And if you can imagine having a piece of paper there, for example, and you would see a dot of light on that focal plane that would be the image of the star. Okay, the distance between the lens and the focal plane is called the focal length, and it is determined by the radius of curvature of the lens. So basically, if you have a very big lens with small curvature, then the focal length will be long. If you have a smaller lens with a smaller radius of curvature, so it's curved more, then it will bend the light rays more significantly, and the focal length will be smaller. So let's complicate things now and add light from a second star. So the second star is somewhere in the sky, but obviously at a different location than the first. And so its rays come to Earth in parallel, as parallel rays as well, but coming from a different direction. And so you can see that represented here, just because the orange rays are parallel to one another, but coming from a different location in the sky. So they pass through the same lens, and they are similarly refracted. Moreover, the lens is characterized by its focal length, which is just that it is what it sounds like. It's the distance over which the light rays are bent enough that they come together to a point. And so that focal length is the same. It is, again, it's a characteristic of the lens itself. And so it doesn't care which image it's forming. All of those images are going to be formed on the same focal plane. And so the upshot is that these rays came from two different stars in the sky. They're refracted through the same lens, and they form images on the same focal plane, but obviously in different locations. So, this is, it starts to get pretty cluttered even with just 6 rays drawn here. In reality, you've got, hundreds of stars that might be visible in a particular region of the sky, say, and so in reality there are going to be a whole lot of light rays crisscrossing each other, and that's fine. I'm not going to, not going to make your head hurt by drawing that here, but you're going to have a number of different images. However many stars are out there, you're going to have those images on the focal plane. Moreover, if you have a different telescope with a different focal length, then the distance over which those rays are focused will be different. And so here in part B, I've added a separate schematic just with a longer focal length. So you can see, as I mentioned just a little bit ago, the lens, the focal length is totally determined by the radius of curvature of the lens. And as usual, there are mathematical relationships there that if this were a course in optics, we would dive into, but mercifully we won't do that. But you can see this in part B. The lens has a larger radius of curvature, that, which is just a way of saying that if you were to continue this, this is part of a circle. It's a circular arc here. So if you were to continue that circle, the radius would be larger in part B than part A. It's not curved as much, and so it takes a longer it produces a longer focal length. It takes longer for those rays to be focused down to a point. So to continue with the basic sort of attributes of a refracting telescope, refracting telescopes, again, I'll say this a few times to hope that it sinks in. Refracting telescopes, just by definition, are ones made with lenses. And typically, they have two different types of two different lenses in them. The first is called the objective lens, and that's the one that we've referred to so far. That's the one through which the rays, are focused. And in this schematic, you can see the rays come from some distant object. They pass through the objective lens and are focused down to a point here. But then a little bit beyond the focal point, so those rays have converged, and now they start to diverge again if they continue on past the focal point. They then pass through what's called a secondary lens, which is in the eyepiece. And then that secondary lens refocuses the light to a new focus, a new focal plane, which is hopefully where you'll put your eye in order to see it. So telescopes, obviously this is the kind of setup that you would have for a backyard telescope, one that that you or I would set up, and you'd want to actually go put your eye in it and look at it. For today's modern telescopes, ones that are used in cutting-edge research and so on, they are not ones where people actually put their eyes, up to, and so the secondary lens isn't necessary. So, if you're just going to use a computer to capture the data and store it and analyze it and so on, then you don't need this eyepiece, obviously. But if you want to actually see something and enjoy it yourself, in real time, then you want the secondary lens, to focus it onto your eye, because that's what you're going to use to observe. So as we mentioned in the context of the pupil and the aperture, the aperture again is the name for the opening through which light is collected, and a bigger aperture / a bigger objective lens means more light is collected, right? There's no magic to it. There's some light coming from these objects, and the bigger the aperture is, the more light you can collect. And the aperture is going to be characterized by its diameter. Typically, you wouldn't need to have a circular aperture, but if you had something that wasn't circular, it would introduce complications that you wouldn't like. So the apertures that we're going to always talk about are going to be circular, And so you could specify the radius if you wanted, but typically the apertures are specified by diameters, and so that's what we're going to do. So refracting telescopes are what started off the astronomical explosion back in the 17th century, and they've served themselves. They've served us well. The largest refracting telescope in the world is the Yerkes 1 meter telescope. Happens to be in Wisconsin. And when we say 1 meter, what we mean is that is the diameter, that's the aperture, that's the diameter of the lens. So a meter is 39.37 inches, just a little bit over a yard. And so if you can imagine a lens, which is a yard, or a meter in diameter, that is a really big piece of glass. And we're going to get to that because it turns out that pieces of glass that big are not easy to make in the very, well, you can make a piece of glass that big, but it's hard to make a very high quality piece of glass that big that is good enough to make good astronomical measurements with. And it gets really darn heavy too. I don't know if you think of glass as being dense, but it is. And so when you have a meter, a meter diameter lens, that's a whole lot of weight. But this is a picture of the telescope. Unfortunately, it is not, actually it still exists, but it is not currently in use as of the last time that I checked. I think there's some refurbishment that may need to be done to the site that it's located at, and last I saw it was unclear whether that was going to happen. So this is the largest refracting telescope in the world, but I'm afraid it's not being used right now. Hopefully it will be again in the future. So I haven't said this explicitly yet, but I guess now is as good a time as any, but I've alluded to it. Refracting telescopes were the first type of telescope, but they are, as it turns out, not the most common type today, and there are a few reasons for that. The first, I just sort of alluded to, but I'll say it now clearly, there are physical limitations to the size, to how big you can make a refracting telescope, and there are a couple of reasons for that. One is, remember, the bigger the lens that you make, for practical reasons, it tends to require larger focal lengths because you can't make an arbitrarily, it's hard enough to make a very large lens. To make a very large lens with a large curvature is even harder. And so you have these large lenses, they tend to have long focal lengths. And this is already a pretty unwieldy focal, sort of thing. I mean, you look at the focal length here. For scale, there's a guy standing next to here. If he's about 6 feet tall, I mean, you can kind of tell this is a really long tube. Okay, that gets pretty difficult to move. Okay, and just to practically point at anything that you would want to see in the sky. The second thing I've mentioned as well, the lens gets ridiculously heavy. Okay, and as it turns out, that it's not just hard to like mount it up there and put the whole thing together, but now it tends to make the steel assuming that they use steel for the tube here, eventually gets heavy enough that it puts undue strain on the steel and will actually make it fail over time. And so just practically, there really are limitations, and the Yerkes telescope basically gets to that point. In order to make anything bigger, it would be so expensive and so difficult to manage that it just becomes impractical. Beyond that, though, there's actually some physics limitations as well, and in particular, there's a phenomenon known as chromatic aberration. And as this schematic indicates here, the big thing here is that different colors of light are actually refracted at slightly different angles through glass, and well, through anything. And the reason is that the speed of different colors at different wavelengths of light are actually slightly different in media. In a vacuum, all wavelengths travel at the speed of light c. In media, they travel very nearly the same, but not quite. Okay, and so as a result, when these rays come in from this distant star, it's going to be a mixture. It's going to be a continuous spectrum in general, and so it's a mixture of all the different wavelengths. But as they refract through the glass, then those wavelengths get dispersed. They spread out. And so the result is that what we've so far referred to as a focal point is in fact not a single point anymore, because the blue light has one focal point, the green light has a different focal point, the red light has a different focal point. Now, this is not drawn to scale, okay, so it's not as bad as what's represented here, but it gets worse and worse as the lenses get bigger, because the bigger the lens is, the longer the focal length, the larger the distance over which these rays can diverge from one another. And so if you have a small lens, then the difference between the blue focal point and the red focal point is so small that for all practical purposes they're the same. But as you make the lens bigger and the focal length gets larger, now these different colors, focal points, end up becoming noticeably different. And the result is that the image that you form is sort of skewed in color space. The colors are not reflective of the original of what the star itself is. And so again, in the spirit of not being creative with our naming schemes, we call that chromatic aberration, because you have an aberrant color that you've produced. And so just to give you an example, looking at Jupiter, it's really it's a stark effect here. I mean, you're used to I'm sure you've seen pictures of Jupiter before. These are not the highest resolution images out there, certainly, but you can see on the right, that looks like Jupiter. You can see the bands of clouds, and you would probably recognize that as Jupiter. Whereas here on the left, with chromatic aberration, it's pretty fuzzy, right? I mean, the colors are all kind of merged together. It's not that it's not kind of a cool picture still, but it's definitely not true to what's out there. And so this is a very serious limitation. You might have thought, when it comes to just weight and length of things, you say, well, okay, it'll cost a lot of money, but we can find ways to engineer solutions to the practical problems of making very large refracting telescopes. But this is physics. It comes from the physics of refraction. And so there's no way to get around this. And it just gets worse and worse as the lenses get bigger. So the question now is, okay, what are we going to do? I just told you that we got from 1610, when Galileo first took, his telescope and pointed it up at the sky, and we made it into the 20th century with the Yerkes 1 meter telescope. But I've just told you that basically we've hit the limit now of what we can do in terms of refracting telescopes. So does that mean that we're just done, that we're going to close up shop and end the semester early? So unfortunately for you, no, that's not the solution. That's not the result. Fortunately for astronomers, there is something else. And as you might have guessed from this slide, the something else is what's called a reflecting telescope. So as you probably guessed, a reflecting telescope doesn't use refraction to bend rays. Instead, it uses reflection from a mirror. And so whereas refraction used a lens to bend the rays, reflection is very straightforward. That's something you're familiar with. You have a ray of light come in, it hits a surface, it reflects, and what's called the angle of incidence, which is this angle here, is equal to the angle of reflection. Somebody somewhere decided to give that statement, that sort of obvious statement, a fancy name, and called it the law of reflection. So the angle of incidence is equal to the angle of reflection. And the great news about reflection is that the law of reflection is true for every wavelength equally, right? So I told you that when it comes to chromatic aberration, that exists because different light rays refract differently. Different wavelengths refract differently. Every wavelength reflects the same, and it reflects at the same angle that it is incident at. So immediately, if we can find a way to design a telescope using reflection, we know that chromatic aberration will not be an issue. So the question now is, well, how are we going to use reflection to focus the rays? Because remember, focusing is the job. That's the task at hand. When we're designing a telescope, we need to focus these parallel rays into a point. And it turns out that the way to do that ideally is with something called a parabolic mirror. And so if you remember your Algebra 2 days and your study of conic sections, a parabola is one of the conic sections. And it turns out that, and you can prove this mathematically if you like to, it turns out that a parabolic mirror is the correct shape to perfectly focus all of these rays down to a point. And so it's a little bit more complicated in the sense that, you know, we could draw our schematics very easily using a refraction mechanism, and we could see how these rays get focused down to a point, and you put a screen there, or you put a secondary an eyepiece, you know, lens, and then you can kind of stick your head down there. It's a little bit more complicated with a refracting telescope in the sense that you've reflected, or with a reflecting telescope rather, you've reflected those rays back onto one another, and so they do come to a focus, but that focus is kind of here in the middle of the system. But you know, people have spent enough time thinking about it that this works quite well. And so, as it turns out, and this is almost guaranteed to come up on a test question at some point, reflecting telescopes are the more common sort of telescope now because they avoid chromatic aberration. And as it turns out, it's much easier to make a high quality mirror than it is a high quality lens. Grinding grinding glass down into precise shapes we can do it, but it's not easy, and it's especially not easy when the lenses get larger. Mirrors, it's much easier, and in fact, mirrors don't have to be made of a single section even. They don't have to be, especially as they get larger and larger, you can actually construct sort of a large mirror out of multiple pieces. And it's much lighter as well because you don't have this huge piece of glass now. You just have some thin, you know, piece of some silvered surface which reflects light. So reflecting telescopes have been around for a long time. Okay, so I kind of presented this initially by saying, you know, we started with refraction telescopes, and they were around for a long time and developed, and that's true. But reflecting telescopes did appear about 50 or 60 years after the first telescopes of any kind, right? And as it turns out, Isaac Newton is the first person known to have designed and built a reflecting telescope, and he did so in 1668. And schematically, it looks kind of like this. So again, you start off with these, you know, parallel rays coming from the distant star. There was a primary mirror in the back of the telescope, which was, you know, shaped carefully, and that reflected light back to a secondary mirror, which then reflected it into an eyepiece. And that eyepiece would still use a lens, right? Because if you put a mirror here in the eyepiece, then you just reflect the light back into the telescope and you don't see anything, so that's not very useful. So you can't have an eyepiece lens here. But this is kind of the schematic of what Newton designed in the mid-17th century. And there are other designs. So this is something that if you were like really excited about the detailed design aspects of telescopes, there's a whole lot of stuff out there, and so you can certainly get into that. We're not going to study that in a whole lot of detail here, but the point is that there are different options here. In this case, you've got the primary mirror is again at the back of the tube, but then it reflects to a secondary mirror, which is here kind of in the middle, and then that reflects it back, you know, towards the eyepiece again. So different designs, but it's the same basic features. You have a primary mirror, you have a secondary mirror, and again, you're using reflection, not refraction, which means you avoid the problems with both chromatic aberration and the problems with these really heavy and unwieldy, very large refracting telescopes. But just as with the refracting telescopes, the power of the telescope is going to be determined by the diameter of the aperture. So there's no lens here, right? It's a mirror, but again, the size of that mirror is what's going to determine how much light is being captured and focused. And so the diameter of the mirror is going to be the sort of the most important piece in determining the power of the telescope. And as I said, it's much easier to make a big mirror than to make a big lens. And so that's one of the main selling points of these reflecting telescopes. And these things can get truly enormous. So here's one of, this may or may not look like a telescope to you, but it turns out it is. It's the Gemini telescope in Hawaii. It's got a diameter, its primary mirror diameter is 8 meters. Okay, so I mentioned, the Yerkes telescope is the largest refracting telescope in the world. It had a diameter of 1 meter, and you basically can't get any bigger than that. Well, we've got a primary mirror that is 8 times that in diameter now, and as I said, avoids the problems with chromatic aberration. So there's really no contest, at this point in terms of, if you want to have a backyard telescope, you could go either way. It is more common to find reflecting telescopes than refracting telescopes for backyard applications, but you can certainly find either, and either would work. But when you want to get to the cutting edge of today's astronomy and really make new discoveries, there's just no way around it. It's got to be a reflecting telescope. And here's a schematic of the Gemini telescope. These things, when they get big, they get complicated. And so lots of engineering and lots of details. And if you're interested, you can certainly go find out as much or more than you ever wanted to. Another very famous telescope pushing the boundaries of astronomy today is the Keck telescope, also in Hawaii. It has a primary mirror that is 10 meters in diameter. And as you can see kind of from the schematic here, it is constructed in segments. And so it's not just a single continuous piece of mirror, because while those are easier to construct than very large lenses, it still gets pretty difficult, and unwieldy to construct a single continuous mirror that is, say, 10 meters in diameter. But it can be produced out of hexagonal segments, as it is here, and work just as effectively. So let's talk a little bit about angular resolution. So I mentioned angular resolution as one of the most important characteristics of a telescope or your eye or any optical device. And certainly you hear about resolution all the time when it comes to TVs and computer monitors and so on as well, because a higher resolution gives you a better picture, right? You can see more things more clearly the higher the resolution. And so this is just a particular example where you can see if you have two sources of light, stars for us, but these could be headlights on a car or anything else. At low resolution, these things tend to merge together, and so you find yourself squinting and kind of trying to figure out, is this one thing? Is it two things? Is it 5 things? What's going on here? Whereas with high resolution, you have sharper edges, less fuzziness, and you can clearly distinguish, okay, these are 2 different light sources. Telescopes with larger apertures have better resolution. Okay? You collect more light, you focus it down, you get a better resolution. And so that's why, in general, the push, to discover more, to learn more about the universe is, almost inevitably a chase to produce larger telescopes. Telescopes with larger apertures, which means larger mirrors, in order to have better resolution. Because if we look out 14 billion light years into the universe, but we don't have good angular resolution, then all we're going to see is a white fuzzy blur, and it's hard to learn a lot from that. So bigger apertures means better resolution, but unfortunately for us, there is also a fundamental limit to the angular resolution that we can get, and that's something known as the diffraction limit. So the diffraction limit is the best resolution that a telescope can theoretically observe. And the reason that such a limit exists is kind of indicated by this pinhole diffraction sketch here, which shows something important, which is that when waves of any kind, as a matter of fact, so this could have been a water tank, for example, that did this experiment. But anytime that waves pass through an opening, those waves diffract. And that means they end up bending as they pass either through a hole in this case, or if they pass around an obstacle. So if you have, for example, if you had water moving through a river and you put a rock in the middle, the waves would diffract as it moves around there. And so because of the diffraction effect, as the light passes through into your telescope, as it moves into the aperture, it will be diffracted around the edges. And so because of that, there actually is a fundamental limit called the diffraction limit to the best angular resolution that you can get. And so, as a matter of fact, if you look at it with a circular aperture, if you look out at a star, for example, what you'll actually see is something that looks like this. You have a central bright point, which is where that object is. But then you have these bright rings, concentric rings that surround it, that are called diffraction maxima. And again, if this were a physics class, we would go into some detail and study diffraction. There's a lot of math you can do there, and there's a lot of things that you can learn. But for our purposes, we don't like diffraction because it places this limit on the resolution. It sort of fundamentally starts to blur things out. Because of the diffraction. And so as you get as you take these two light sources again, they will each have their own diffraction pattern. And so when they're far enough apart, you can see, oh, these are two distinct diffraction patterns, and you kind of wish they weren't there, but you can figure out a way to separate them. But as they get closer, as these objects get closer, smaller, angular displacement between the two, or angular separation, these diffraction patterns start to merge. And so finally you get down to this bottom picture and you look at that, and some people would squint and say, yeah, I think I can see two different objects, but they're close. And other people would look at this and say, no, that's just one object, right? And so this is a good example of how the diffraction limit really does prevent us from getting infinite resolution. So there's another problem that can arise in the context of observations as well, whether you're using refracting or reflecting telescopes. And that's something that is called astronomical seeing. Now, I've made comments several times already that we're not very creative in our naming schemes. I kind of wish we'd been a little more creative here, because I have no idea I do know what astronomical seeing is. I'm telling you what it is, but it doesn't convey a whole lot just by the term. But basically, it's a not very technical term for saying that the Earth's atmosphere distorts what we view. And you may have already heard this, but if not, I'll go on the record as saying stars don't actually twinkle, right? Stars give off light at a pretty darn regular rate. Over lots of years, they may vary some, but certainly when you're looking up at a star, it's not pulsing. Okay. What's happening is that the atmosphere is in between you and the star, and so the star's light comes, who knows how many light years to Earth, passing through the vacuum of space, and then finally, just before it gets to your eyes, it passes through the Earth's atmosphere and gets totally warped. Maybe not totally warped, but it gets warped by the atmosphere. And as it turns out, that effect is what's responsible for setting the resolution limit of ground-based telescopes. So, we've talked about chromatic aberration, we've talked about the diffraction limit, but the diffraction limit, while it does provide a theoretical limit for the best resolution that you could observe, or that you could achieve for a given aperture and wavelength of light, you'll never get close to that with ground-based telescopes because of astronomical seeing, because of the effect of the atmosphere. And while this is not a telescopic image, one example of the atmosphere playing optical tricks on you is given in this picture, where it looks like there's water on the road, right? It's the same thing as a mirage, right? So if you're in the desert, you may look out and it looks like there's water in the distance, and you get excited, and then you get up there and you realize, no, there's no water, and you think, is my mind playing tricks on me? Well, it could be that, yes, your mind is playing tricks on you, but it's also very often just physics here, where the heat of the road is such that the air next to the road is a little bit hotter than the air above it. And so effectively then, from an optics perspective, from the point of refraction, there are two different media, because light travels a little bit faster in the hotter air than it does in the cooler air. And so the result is that just like light bends when, or can even reflect when it moves from one material into another, that can happen as it moves from as light moves from cold air to hot air as well. And so in fact, when you look at this, it looks like you're seeing water. What you're actually seeing is the sky. Light is coming from the sky. It's not even making it to the ground, but is reflecting off of the hot air effectively, and then coming up to you. And so you're looking down and you think you're seeing something on the ground. Really what you're seeing is the sky. So I remember when I first learned that, I thought that was pretty cool. And it's not directly applicable to, we don't normally point our telescopes at the ground, so it's not something that we're going to do specifically here, but the physics is the same. And it's sort of a very clear example of the fact that you're not seeing what you think you're seeing, and because of atmospheric effects. So how exactly does the atmosphere mess with our astronomical observations? It's easy to say it, and I don't think any of you would probably argue with me, but what is actually happening? So these parallel rays come from stars out in the cosmos, and again, they travel who knows how many light years in straight lines, maybe occasionally passing through a cloud of hot or cool gas, out there, but mostly just passing through nothing. And then finally it hits the atmosphere just before it gets to us. So there's uneven heating in the atmosphere and cooling, right? So there are pockets of atmosphere that are hot, there are pockets of atmosphere that are cold, and hot air rises and cold air falls, and so the atmosphere is always moving. There are convection currents, sometimes storms, but there's always, even when it looks like it's clear, the atmosphere is always doing something. When that light enters the atmosphere, then it's going to hit these pockets and respond in, I've said unpredictable ways here. In principle, it's predictable. We understand the physics. It's not like there's new physics here. But in practice, it's going to look very random, okay? Because we can't, you never know when a hot pocket of air is going to come through or a cold pocket of air. And so the result is that you've added randomness into these rays. So they were parallel, but now they're not quite parallel. They're a little bit off kilter because as they move through hot air, they get bent less than they would if they were moving through cold air. And so some rays are bent a little bit and some rays are bent a little bit less. And the result is that when they finally hit your mirror, or when they finally go through your lens, in your telescope, they're not actually parallel anymore. And so instead of having a focal point now, you don't. Okay, or not a perfect one, right? Because the rays are still mostly parallel, but not completely. And so the result is they no longer focus perfectly to a point. They're a little bit off. And so the result is that you get a fuzzy image, okay? And you get one that changes over time. That's the twinkling again, right? Because as the air moves and so on, the rays get jiggled around. And so the focal points get jiggled around. And so the result is fuzziness. And there's just no way around it, as long as you're on Earth, right? As long as you're on Earth, safely ensconced in the atmosphere, it's great for you in terms of like ability to breathe and sort of regulate temperature and things like that. But there's no way around it. It's going to screw up your astronomy. And so that's just something that you either have to accept or try to get around. And there are a couple of ways to do that. The first, and maybe the most obvious, is just get outside the atmosphere. Okay, it's really expensive to do it. It's very difficult technologically and practically to put together something as as fancy as as a high-tech telescope and then launch it into space and then, you know, put it out there in orbit and make sure that it doesn't, make sure it stays in orbit, doesn't crash back into, you know, to Earth. And obviously if something goes wrong, it's a whole lot harder to do maintenance on a telescope that's orbiting the Earth than it is to just walk over to the telescope and tinker with it. But it may be worth it to you if you really want to get over the astronomical seeing and avoid the stars twinkling. So this is an image of the Hubble Space Telescope, which is the largest space telescope currently, though the James Webb telescope is soon to be up there, and that will be larger. But so the easiest way to correct the astronomical seeing or get around it is to just put your telescope up in space. But as I said, it's a very expensive and very difficult prospect. Can be done and has been done, but you can't do it all the time. But there's a second option, which is very recent, but pretty cool, which is known as adaptive optics. And this is something that you could take a whole course in. And if anybody's interested in electrical engineering or in computer science, for example, this would be something that'd be kind of cool to study. But adaptive optics basically is a fancy way of saying we're going to put together what's called an adaptive mirror in a beam splitter and a wavefront sensor, and we're going to write some software, and we're going to figure out what's the true signal and what are the wiggles that are being put in. And basically then, and it's almost like magic, because what it allows you to do is it allows you to take the ground-based signal. You're still on the ground using these ground-based telescopes. You're taking in this fuzzy signal, and you're able to use a program to separate out the true signal from the artificially imprinted signal that was due to the atmosphere, and subtract that away. And this is phenomenal. And so if you look at an example, you've got an image of a star without adaptive optics here on the left, which just, I don't know about you, I look at that, I don't see a star at all. And then as you apply the adaptive optics, in successive degrees, eventually you're able to get just this pristine image where you even see the diffraction pattern, right? Which, like I said, we don't always love diffraction patterns, but they're there. And so the fact that you could recover not just the central peak itself, the central image, but also the diffraction patterns using the adaptive optics is really phenomenal. And that's great because, as I mentioned, it's really expensive to put the telescope into space, and it's really difficult and expensive, again, to provide maintenance to it. Moreover, we've already got all of these ground-based telescopes. And it would really, stink if we just reached the point where we said, okay, these aren't any good for us anymore. So with the development of adaptive optics, we're able to continue to use these ground-based telescopes and still get extremely high-quality images. And there's a great animation here from UCLA that shows the application, again, of adaptive optics to the galactic center. So this is the center of the Milky Way. We're looking in there and trying to get a sense of what's going on there. Without the adaptive optics, you see some bright splotches, right? But that's really all they are, just splotches. Whereas as you sort of refine it with adaptive optics, you see very clearly individual bright spots emerge that are much better resolved, right? And so what started off just as like this red blur in space in this zoom, in the zoom section, really becomes much clearer, much more interesting. And so the development of adaptive optics, like I said, it seems like magic, as so much of computer science does, but it's really phenomenal. So if anybody's interested, if anybody's not interested in that, you should be. But certainly I think that's a pretty exciting thing to probe further in if you're at all interested. Okay, so we've talked about telescopes now. We know there are refracting telescopes and there are reflecting telescopes. We've talked about some of the limitations, both practical and fundamental. So now let's imagine we understand how to build a telescope. We've decided what kind of telescope we're going to build. Where should we build it? Okay, so do we just go build it? Knock down the neighbors' houses, knock down the block of houses, and just build it right there in my backyard, or is there somewhere better? Well, there are a few characteristics that are desirable for where you're going to build an observatory. And the first is kind of obvious, but let's go ahead and say it. It would be good if it were dark. Okay, we're trying to see things that are pretty faint, right, in the sky. And so the less ambient light you have, the better. Okay, so this is a nighttime image of the United States. You can see there's a lot of light in the U.S. There are more dark areas out west than there are in the east. But if you're going to build an observatory, you would like it to be dark, just so that the ambient light doesn't pollute your image, right? And if you've heard the term, light pollution is the term that's used with regard to astronomy anyway, and it is used more generally. You want a dark area so that you can see stuff better. The next thing that you would like is you would like it to be dry, and this might be less obvious. But we've talked about astronomical seeing and the deleterious impact of the atmosphere on our observations. But it turns out that water vapor is particularly insidious when it comes to astronomical observations. So the more water vapor there is in the sky, the worse your image is going to be. And there are a couple of reasons for that. It blurs the images, as we've discussed. It blocks infrared light, which is a problem for infrared telescopes. Again, we tend to focus and tend to think about visible light telescopes, but a lot of the biggest and most powerful telescopes that are used now look at wavelengths outside of the visible range, and so infrared light can be blocked by water vapor, so that's not good. And if you've got moisture in the air, then when you wake up in the morning, it will likely have gotten cool enough that it will condense, and then you'll get condensation on your instruments. Okay, and that's definitely not good, because if the water vapor in the air screws with the light, you better believe that water droplets on your mirror or your lens are going to completely destroy your image. So for all of those reasons, we really don't want water. So if we're going to build an observatory, we want it to be dark, so away from people, and we want it to be dry, so that we don't have these myriad of problems introduced by water. And so as a result, telescopes are often located in deserts. Okay, so those are two characteristics. When you're going to build your observatory, those are two characteristics that you want. And a third characteristic is that it would be good if this were at high elevation. Okay, and that's, again, just a practical matter here. But the higher you are, the less atmosphere you have to see through. As you know, the higher you get in elevation, the lower the density of the atmosphere is. So, and this is noticeable even if you just climb a mountain, right? Or if you go to Denver, the mile-high city, the atmospheric density drops. And so the less air that you're looking through, the less distortion that you're going to have to either just accept or fix with adaptive optics, or and so on. So you'd like your location to be high, you'd like it to be dry, and you'd like it to be dark. And finally, you'd like it to be near the equator, but not too near. Okay? And the reason for that is that in the northern hemisphere, you see certain stars at night, and in the southern hemisphere, you see different stars. If you're near the equator, you see more of the sky. You can see both northern hemisphere and southern hemisphere stars. But, as you probably are aware, the closer you get to the equator, the more humid it tends to get as well. And so, and we've just said that we would really like our ideal observatory to be located somewhere that's dry. And so you're trading things off here, because you don't want all the moisture, you don't want the tropical weather, you don't want rain, you don't want clouds, right? That's another, I didn't mention clouds before, but certainly if you're somewhere where it's wet enough, you're going to get clouds, and that's a total disaster, right, for observing. So, so that's why you would like to be near the equator, but not too near. Okay. And so the gray region here are the tropics, between the Tropic of Cancer and the Tropic of Capricorn. We tend to stay outside of those, so these red dots are just represent particular observatories around the world. You can see there are more in the United States and Europe than elsewhere. There are a few scattered around the world, though. And most of them are outside the tropics. You can see there are a few dots here in Hawaii. Those are up on very high elevations in the mountains, actually up above the clouds in most cases. And so if you have that situation, then you're okay, right? Because you say, well, we're in the tropics, but we're so high in elevation that effectively you've stepped out of the tropics now, vertically rather than horizontally. But you see there are quite a few locations kind of just outside the tropics here in South America, and then again in North Africa. Obviously, you know, these, as I mentioned, these are centered in Europe and Western Europe largely, and the United States, because countries in Western Europe and the United States are first world countries with enough money to build observatories. So that plays a part too, right? So would it be better if we could move some of these observatories to different geographies? In principle, sure, but we do the best we can given the reality of the world we live in. So now that we've built our telescopes, we've built our observatory. Now we want to start taking images, right? So how do we do that? So from the very beginning of astronomy until photography was developed in the 1800s, astronomers would just sketch what they saw. And this is true of all sciences, right? I mean, if you go back to the discovery of the cell and Robert Hooke, he was drawing physically, just with pencil and paper, what he saw. And I have always been very grateful that I was born after the advent of photography, because I have absolutely no artistic talent, and so I would have just been out of luck and never made it as a scientist probably. So for example, the Perseids are sketched here. I don't know if you look at this, if you would see the Perseids, but this is the kind of sketch that that astronomers would make. The big circle represents the sky, and they'd label north, and then they would draw dots where they saw dots. So it would have been frustrating to me to do something like build a telescope and get all excited because finally we could see all these things that no one had ever seen before. And then I realized, well, the only way to share this with anybody or to tell people about my results is to sketch it. And then I would have had to hire somebody else to do the sketch, I guess. But anyway, that's what they did. But eventually, in the 1800s, photography was developed, and in particular, photographic plates were used for almost 150 years, starting in the 1840s all the way up into the 1980s. And a photographic plate is just a piece of glass coated in a silver salt that turns black when light hits it. Okay, so when light hits it, there's a chemical reaction, and it turns, there's a chemical reaction, creates a new compound, and it becomes black. And so if you cast an image onto this plate, the longer you expose that plate, the darker the image will get. Okay, so and that technology developed in the 1840s, was refined, but essentially was unchanged for 140 years until the 1980s. And so we already talked about how we build the telescope. Now, instead of just putting your eye in the eyepiece, you take out the eyepiece and you put a photographic plate, and you get an image on the photographic plate that's exactly a representation of what you would have seen. And so here is, for example, the first photograph of the moon taken in 1840. It's a pretty darn good image of the moon. We get better ones now, but it's pretty cool looking. I mean, and certainly if you think about how much better this is than what you can just see clearly with your naked eye, it's pretty impressive. But as I mentioned, in the 1980s, there was a change, and that change came in the ways of something called CCDs, or charge-coupled devices. These were developed in 1969. It took a little over a decade to sort of, for the discovery to be fully developed technologically and rolled out to the masses. But it was developed at Bell Labs, which, if you're not familiar with, was really a hotbed of science and technological innovation. Various Nobel Prizes came out of Bell Labs. Some of the top scientists in America, came out. Many of them, were at Bell Labs at one point or another. And the charge coupled device, or CCD, was developed in almost overnight. I mean, in terms of scientific development timescales, within a decade, certainly, completely revolutionized both astronomy and photography. So, for example, CCD cameras, they're everywhere now. They were nowhere before this, right? But certainly they revolutionized astronomy, because now we're able to get much higher definition and higher resolution images than we could get with photographic plates. To give you a sense of size, this CCD here, which is large, is about 6 inches across. So, I mean, it's macroscopic, but it's the thickness of a human hair. Okay, so ridiculously thin, but large. Obviously, there are smaller ones too. And here is sort of a night and day example of the advantages, or illustration of the advantages of CCDs. Same image taken with a photographic plate and with a CCD, same observation. And so, whereas with a photographic plate, you've got 2, 3, 4, maybe 5 or 6 dots that you can see. And if you squint, you might convince yourself that there's some other stuff that you can't really tell. With a CCD, it's mind-boggling, in terms of what you can see. There's so much more there. And so certainly if you're a photographer and you're just wanting to take high-quality pictures, certainly it's a no-brainer to go with a CCD. And same thing, if you're an astronomer trying to get an accurate representation of the sky, it's just CCDs. I don't know whether you can say it's as much of a difference as it was going from the pre-telescopic period to Galileo's telescope, or not, in terms of just opening up the so much more of the universe to observation. But the CCD is, I mean, there's a reason they won the Nobel Prize for this. I mean, this really is it just takes it to another whole level, what we can observe. And the reason is just that CCDs are much more sensitive to light than the photographic plates. The photographic plates, they rely on this chemical reaction. You have to have enough of those reactions occur to make a dark enough spot that you can clearly see it. They can bleed. The images are not nearly as sharp. Whereas the CCDs, they're digital in the sense that you've got these individual cells that make up the CCD. And each cell is either activated or not. It's either light or dark, and we can put a whole lot of those onto a single CCD, and so that's what allows us to get such high resolution. So people do spend careers, learning and applying the details of that technology. We're not going to do that. We just need to recognize and appreciate the fact that the development of the charge coupled device really did revolutionize our ability to get high quality, very high definition images. So there's another tool that we spent most of the time today talking about telescopes, but there's another tool that we're going to refer to periodically, and particularly over the next several lectures, where we will move on after today into analyzing starlight. And one very important tool in that context is called a spectrograph. And it's a device that just splits light into its components. Okay, so white light is the combination of all colors, right? All different wavelengths. But it turns out that we're going to be able to get a huge amount of information out of the light by splitting it up into its components and seeing how much of this wavelength do we have, how much of that wavelength do we have. Are there any wavelengths that are missing, for example? If you think back to absorption line spectra. So Basically, the way a spectrograph works is that light comes in through a small slit in the telescope's focal plane. So again, whether you're using a refracting or a reflecting telescope, light is focused to a focal plane. You then use a mirror to reflect it onto something called a diffraction grating. And there are a couple of different ways of making diffraction gratings, and we won't go into the details there. But the point is that it's something that splits light up into its colors. So, a prism does that using refraction. Turns out you can split them up using diffraction as well, and that's what a diffraction grating does. And then you use another mirror to reflect that, the diffracted light now. So you've separated out the colors, the different wavelengths. You capture that with a CCD, and you use some fancy computer software, and you can analyze exactly how much of this wavelength, how much of each wavelength do you have. And going forward in the next couple of weeks, we'll talk in a lot of detail about how we can use that information to figure out what the heck the stuff is that we're looking at. So as I said, the diffraction grating splits light. Maybe I shouldn't say just like a prism. It splits it. They both split it, but they use different techniques, right? Diffraction is the bending of light when it passes through a slit or past an obstacle, whereas refraction is the bending of light as it passes from one medium into another. So both achieve the same results in terms of separating out light. Sometimes diffraction is more easily applied. Sometimes refraction is more easily applied. Just depends upon the application. But a spectrograph here uses a diffraction grating. And as I mentioned, telescopes, we tend to focus on the visible range or the visible spectrum when we're thinking about them, and certainly when we're visualizing them, because that's what we can visualize. But after the discovery that visible light is just a very small sliver of the electromagnetic spectrum, it happens to be the sliver that humans' eyes are attuned to. It didn't take scientists long to realize, well, we might not be able to see these other wavelengths, but if we can detect them, we might be able to get a lot of information out of them. And it turns out that's true. And so I'm certainly not going to read all of this slide to you, but I hope that it will convey to you the fact that astronomers do actively now use essentially the entire electromagnetic spectrum. And so we've got, for example, on one end of the spectrum, we've got the Fermi telescope, which looks at gamma rays, which are the highest energy. It's the highest energy portion of the electromagnetic spectrum. They are, and so the Fermi telescope is outside the atmosphere. It's in orbit because those gamma rays don't survive the atmosphere. On the other end, we've got a lot of radio telescopes around the world, which are what they sound like. Instead of detecting visible light, they focus on radio waves. And then we've got everything in between. Okay. One thing that's interesting and worth noting is that if you look at the transparency of the atmosphere here as a function of the wavelength, it varies a lot, right? So the atmosphere is opaque to these very short wavelength electromagnetic waves. So light is absorbed. This light is absorbed by ozone and molecular oxygen, of which fortunately we have quite a bit. Not the ozone. We do have some ozone, but we're fortunate to have plenty of molecular oxygen in the atmosphere. So that oxygen just it takes care. It knocks out all of these, the X-rays, the UV, and the gamma rays. Visible light gets through the atmosphere, right? That's why it's visible. If it didn't, then it wouldn't be. But and you can see there's wiggles here. So it turns out there are some wavelengths where the atmosphere is basically transparent to it, and then there are nearby wavelengths that is basically opaque to it. This is entirely dependent upon the electronic structure, the energy levels of the molecules in the atmosphere. So if you wanted to calculate this thing, that would be a very Herculean task involving supercomputers and so on. But it's totally determined. What wavelengths get through and what wavelengths don't is just determined by the atomic and molecular energy levels of the stuff in the atmosphere. Then there's something called there's an opaque region here where these wavelengths don't get through. And then we have what's called the radio window, where radio waves are very transparent to the well, the atmosphere is very transparent to radio waves. And then finally, if you get to very, very long wavelength radio waves, a little bit above 10 meters in wavelength, the atmosphere is opaque again. Okay, so as a result, there's some things, some wavelengths that you can observe effectively on the Earth, and there are other wavelengths that you have to be out in space to observe. And so we deal with what we got as best we can. So we send spacecraft out, and we're getting near the end here, so I'm just kind of giving you a couple of final tidbits here. The Voyager spacecraft, for example, launched in 1977. It's on its way out of the solar system, is now out of the solar system, depending upon how you define a solar system. But it's made various observations over decades as it moved on past every planet there is. Finally, got an image of Pluto here, which is no longer a planet, but still worth an image. We also send, and if you're wondering what on earth any of this stuff has to do with telescopes, remember the actual title of this lecture has to do with just the technology, everything that we use to sort of investigate. And so most of that is telescopes, but we also have some other things. So now we have some Mars rovers that go and actually walk, not walk, but roll around on Mars and try to dig up dirt, for example, if you've seen that's been in the news recently. And so these are things that obviously are pretty restricted to nearby objects. It's hard to go to a star, but for the planets that are nearby, we can do it. And then finally, we do have some sample return missions. Strictly restricted to the moon, because that's the only thing that has been near enough for us to go to and come back. But we've got moon rocks, and we can analyze those. And people are continuing to, scientists continue to analyze moon rocks that were obtained decades ago. So anyway, I appreciate your attention. I know there was a lot of material there, but the good news is that we really are now transitioning from the background knowledge and building up a base to really starting to analyze light. And so in the next several lectures, we'll be analyzing starlight and finally getting to the point where we're using all of the knowledge that we've developed so far to extract as much information as we can out of the light that the universe sends our way. So thanks for your attention, and I will look forward to getting back with you in the next lecture.